Okay, good morning, students. Myself, Dr. Omkar Singh. I will be taking this course on digital signal processing. I hope you are all doing well and you will enjoy this course. So, today we will discuss in the introduction about what we are going to study in this course in the entire semester. So, I will broadly give you an overview of the topics that we are going to cover in this course. Okay, so the course contents for this course major topics that we will see. First of all, for DSP, the signal and systems course that we have studied earlier, it is a prerequisite course to study the DSP. Okay, so we will have a review on the basic concepts that you have studied in signals and systems. Okay, and in this topic we will cover some basic concepts like what is a signal, what is a system, and how the continuous time and discrete time systems they are different, and how the continuous and discrete signals in fact they are different. Okay, the focus in this will be basically on two important signals. One is the complex exponential and the second is the sinusoidal signal, sinusoidal function. Okay, we will study both these signals in continuous time as well as in discrete time, because these signals they are very important as they are the building blocks from which any other signal can be generated. Okay, so we will discuss in detail about these two signals, the complex exponentials and sinusoidal functions, sinusoidal signals for both continuous time and discrete time case. Okay, so there are some other classifications of signals that we have already studied, so I will not go into that detail, but these two signals we will cover a bit in more detail. And then there is a system which is used to process a signal. So there are different types of systems that we have studied. We will take a overview on that, like linear system, time invariant system, static and dynamic system, stable and unstable system, and so on. Okay, and another important classification of signals that we use in DSP is digital signals, the difference between the analog and digital signals, and how your digital signal processing is different from analog signal processing, and what are the advantages why we go for the DSP as compared to the ASP, that is analog signal processing. Okay, so in this category signals, when you define a signal is generally defined as a source of information. Okay, it may be any signal whether it is a speech signal or a voice signal or a biomedical signal or a image signal or a video signal. Every signal has some information, and what is the purpose of signal processing is to extract this information from the signal. So mathematically signal is defined as a function of one or more independent variables. Okay, so signal is nothing but a function of one or more independent variables, and this independent variable can be anything. It can be time, it can be position, it can be height, it can be temperature. But when we define the signals in electrical or electronics domain, the independent variable is generally a time. So you have some voltage or current maybe that is varying with respect to time. Okay. Otherwise, if you take a suppose, so you have on this axis time and you have a function of time. Okay, this is maybe the amplitude of the signal, and this varies with respect to time. This is what is a signal. Okay, and this is basically on the y-axis you may have a voltage or a current, and that is a function of time. Okay, but when you say suppose if you have an image signal, which is a two-dimensional signal, so we have x and y coordinates which are called as spatial coordinates. So at any point of time, the pixel value or the intensity, it is a function of two variables x and y, that is the space coordinates. Okay, so this becomes a two-dimensional signal. Now in this case, the independent variable is generally not time, but it is a function of the space coordinates. Okay, if you take video signal, in that case along with space you have time also, so this becomes a three-dimensional signal. Okay, so generally in DSP, in one-dimensional signal processing, we are concerned with signals which have a variation with respect to time. Okay, when you go for the two-dimensional processing, we take the input signal as a image which is a function of two variables. Okay, this is what is a signal, and every signal has some useful information in that. So when you process a signal, we try to extract that information which is embedded in the signal. Okay, so you pass a signal, so you have a signal, and then you have a system. So you have input signal, you pass it through a system, you have a output signal. So this output signal we call it as a processed signal, because we have applied some signal processing on the input signal, which is maybe a raw signal, and you try to extract some information from this signal. So this, before you study the properties of the system, you must fully understand the properties of the signal itself. Okay, so once you understand the properties of the signals, then you can design a corresponding system to process that signal, right? Now in the classification of signals, there are many classifications like one-dimensional and multi-dimensional, single channel, multi-channel, continuous time, discrete time, analog and digital, random and deterministic signals, and so on. Okay, so the major two classifications in the signal theory that are important for this course is, one is your continuous time and discrete time signals. Okay, so when you say continuous time, it means the independent variable, that is t, it is continuous in nature. So you can have the signal information at any instant of time that you desire. Okay, so when the time is continuous, the signal is called as continuous time, whereas in discrete time, the signal is not present at each and every instant of time. The time axis is basically discretized. Okay, so you may have signal at this time, then after some time t, you have this may be the value, then maybe after some time 2t, we have another sample, then after some time 3t, you have another sample, and so on. So the time axis is not continuous, it is discretized. So the signal values, they are available only at a particular instant of time, not continuously. This is what is called as a discrete time signal. Okay, so this t may be anything. It may be suppose 0.1 second. So you have one sample at 0, then you have after a time of 0.1 second the next sample will be at a time interval of 0.2 second, then 0.3 second, then 4 second, and 0.4 second, and so on. Okay, so these type of signals, the discrete time signals, they are normally not encountered in, you can say, real life. Most of the signals that you acquire, they are continuous time signals. But when we use DSP, we process only discrete time, or in fact digital signals. Okay, so discrete time signals, if you process a discrete time signal, you have a discrete time system for that. And if you process a continuous time signal, you have a continuous time system for that. Okay, and you will see that when we use DSP, the very first step is to convert a continuous time signal into a discrete time signal before you can process it further using a discrete time system. Okay, so this classification is straightforward based on the time axis. If time is continuous, your signal is continuous time. If time is discretized, your signal is a discrete time signal. Now this type of signal, suppose you can have maybe if you suppose measure the blood pressure of your body, the BP. Okay, after suppose say every half an hour. So you start from some time at this point and you measure your blood pressure. Suppose it is 120 by 80 mmg, millimeters of mercury. And then after 30 minutes, this T, which is now 30 minutes, you again measure your blood pressure. So you get another value here. This may be different. You may get here now 120 by 70. Okay. Then after 1 hour, that is 2T, you again measure your blood pressure. You get some other value and so on. So the signal is not continuous in time. So you have discrete samples. Okay, after a specific time interval, you have the sample values. So this signal basically nothing, but it becomes a sequence of numbers. Okay, the time information in this case has no significance, or you can say that the time information is lost. Okay, so you have like suppose if I take the signal, this may be have a amplitude here 2, it may be 1.5, it may be again 2, it may be 1.6. So you represent a discrete sequence xn to 1.5 to 1.6, so on. Now these are just samples. Okay, you have no time information. This is sample at n is equal to 0, this is sample at n is equal to 1, n is equal to 2, n is equal to 3, and so on. So now this n is equal to 1 is not basically time, it is a sample number. Okay, this n is equal to 2 or 3, they are not the time values. But anyhow, if this signal is generated from a continuous time signal, then you must have the knowledge about what was the sampling time. Okay, after which time interval you have taken the samples of this signal, because that is very important in case you want to convert back this discrete signal into the continuous time signal. Okay, so in continuous time signal, which are denoted by xt, and time is a continuous function, discrete signals, they are denoted by xn, where n denotes the sample numbers. Okay, n is not no time in this case. The time has lost its significance in discrete time. In fact, xn is nothing but just a sequence of numbers, and moreover, this n can take only the integer values. It cannot take fractional values. Like in this case, t can be 1.2, 1.4, 2.5, but n has to be discrete and it has to be integer, that it may be 0, 1, 2, 3 and so on, or it can take negative values also, -1, -2. Okay, this is one classification of signals, that is continuous time and the discrete time signals. Another important classification that we have, it is analog and digital signals. Analog versus digital signals. So this classification is totally different from continuous time and discrete time. When you classify the signals into analog and digital, we basically look at the amplitude axis, not at the time axis. Okay, suppose I plot two signals. This is x1t, this is x2t. Okay, this signal is supposed like this, and one signal, this is like this. Okay, so this signal, if you look at the amplitude of this signal, it can take only two levels here. This is suppose level A, and this may be level B. So the signal amplitude, it fluctuates between the two levels, either at level A or level B. So when the amplitude of the signal is fixed, or it takes certain fixed levels, we call it as a digital signal. Okay, and if the amplitude of the signal is changing randomly, it can take any value, it is called as a analog signal. Okay, so and similarly, and see, both these signals, they are continuous time signals, and you can have the same classification in discrete time also. So if you take a signal like this, and one signal like this, okay, again in this case the signal voltage levels, they are fixed to two levels, either this is the sample value or this is the sample value. Okay, but in this case, again, the amplitude of the signal, it changes randomly, it can take any random value. Okay, so this is again a analog signal, this is again a digital signal. Okay, so in the digital signal, it is not necessary that the amplitude can take only two levels. This is a special case which we call as the binary signal, but in general the number of levels must be fixed. It may take 4 levels, it may be 8 levels, it may be any other levels, but the signal amplitude cannot take any random value. It has to take a value that is predefined. You have a set of predefined amplitudes, and at any time the signal must take one of those values. That is what is called as a digital signal. Okay, so if the amplitude can take any value at any instant of time, this is what is called as analog signal. Okay, so this is a very important class of signals that we generally use in the DSP, digital signal processing. Okay, it means the signal which we use for DSP processing, it is discretized in time axis as well as discretized in the amplitude axis. Okay, so first we discretize the time. When you discretize the time, the signal converts from continuous time to discrete time, and then when we discretize the amplitude axis, it becomes a discrete time digital signal, right? So this is these two classifications, they are very important. And now see how you use DSP, or how DSP is different from analog signal processing. So in the analog processing, analog signal processing versus digital signal processing. Okay, so you have analog signal xt, which is continuous in time, and the amplitude of the signal is continuously changing with time as well. So there are two ways to process the signal. Either we use a analog system here to process the signal directly. The output of this system will also be analog signal. Okay, so analog circuits that you have studied in analog electronics, maybe you use a circuit using operational amplifiers, or maybe using transistors, or there are other circuits like 555 timers and so on. So those kind of circuits, they are used to process analog signal. Okay, now in the digital signal processing, what we do, we have a input signal which is continuous time and analog signal, because in the real life the signals that you get, they are mostly in continuous time and analog signals. You hardly get a digital signal in real life. Okay, but we process the signals in the digital domain, although the signal is analog in nature. So how we do that? The first thing is that you have to convert this signal into a digital signal. So you need a device which is called as analog to digital converter. Okay, so at the output of this, your signal will become digital, and then you have here digital signal processing, DSP. Okay, so the signal is now processed in digital format, and if you want to convert back this signal into the analog domain, you can interface here a D to A converter. You will get a analog output. Okay, so this is also digital, and this is analog, and input is analog. So these are the basic blocks in a DSP system. So you have an analog signal, you have a to D converter, this converts analog into digital signal, and then you have a DSP algorithm which processes the digital signal as per the design, okay, which was designed in the system, and then you get a digital output. So this digital output, you may store it or you may display it as it is, but if you need to convert this into the analog signal again, you have to interface a D to A converter. Okay, so it means even you have an analog signal, you have another means to process the analog signal using the digital signal processing. Okay, now this A to D converter, analog to digital converter itself, it has many blocks within it. So you give input a continuous time signal, analog signal. The first block that you have, it is a sampler which converts the continuous time signal into a discrete time signal. Output of this is discrete time. You have discretized now the time axis, but the amplitude is still analog. This is not a digital signal, this is a discrete time signal. And once you have discretized the amplitude, the time, the next what we do, we discretize the amplitude using a quantizer or a quantization. Okay, so there are the output of this, you get a signal which is discrete in time, which is discrete in amplitude, and then you can convert this signal finally into a binary format using a coder. So this binary coder will generate a binary code for each amplitude. So finally you have a signal in the form of zeros and ones, which is a digital signal, the binary signal, and this signal will go into the DSP block and it will be processed, and your output, it may be converted into analog again using a digital to analog conversion. Okay. Now see why we choose, why we prefer to choose DSP over analog signal processing. The main concept behind this is that, see, when you define a system, we have defined a signal as a source of information and mathematically as a function of independent variable, which is time. Okay. Now when you have a system, so system is basically a physical device. A system is a, you can say, a physical device used to process a signal. Okay. So you have a device or a circuit which processes a signal, that is called as a system. Okay. And this circuit or this device may perform any function depending upon what type of signal you have and what you want to extract from it. Like suppose if you have a communication system, so you may have a input signal and then you have a carrier signal, so you modulate it, so the modulator becomes a system. Okay, so output of the system you will get a modulated signal. It may be a biomedical system in which suppose you have input a ECG signal and you have a heart rate HR monitoring system. So the purpose of the system in this case is to compute the heart rate from the ECG signal and maybe displayed on some device. Okay, so ECG is a raw signal, it contains many information, but what is the purpose of the system here is to get only the heart rate from the signal, and that has to be displayed. Okay, and similarly you may have an image signal and you want to compress the image. Okay, so you have a image compression system, or when you take image, the image is suppose blurred and you want to remove the blur from the image, so you have a different system for that, right? Now in the analog system processing or analog signal processing, this system is always a hardware. It is always a hardware circuit. Okay, designed from various analog components, electronic components. But when you see DSP in the digital system processing, this system is not generally a hardware. It can be a hardware or it may also be a software. That is, you have DSP processor here. Okay, so this is a flexibility in DSP which is not available in the analog signal processing. So when you have to use analog signal processing to process any signal, you have to design a hardware for that analog circuit. But when you want to process analog signal using the digital signal processing, first you need to convert this into a digital format using the A to D conversion, which contains sampling, quantization, and coding. And then you have a DSP system which can be implemented in hardware using the digital logic circuits that you have studied, maybe using logic gates, multiplexers, flip-flops, shift registers, and so on. Or it can be simply a DSP processor. So you write some code in the processor and that code will process this input signal and it will generate a output signal. Okay, so this is the flexibility in DSP which is not available in your analog signal processing. Okay, so by simply changing the code in the DSP processor, this block can be used for many applications. Whereas in the analog signal processing, if you want to design a new system, you have to design a new hardware, you have to test it, and then you have to implement it. But that is not the case with the DSP system. So by just changing the code in the DSP processor, you can implement so many systems. You may design this system to be a filter which is used to remove maybe the noise from the input signal, or this may be a system which is used to find the correlation between the two signals, or anyway anything you can implement. Okay, so this is the major advantage of why we use DSP over analog systems. So it has a flexibility. Okay, flexibility in the sense that you can implement the system in either hardware or in software. And another important advantage you can say that is that the DSP systems, they are somehow more cheaper as compared to the analog systems. And another thing is that the tolerance is also a factor. It is very difficult to control the tolerance in the analog circuits, that you know. Okay, but in digital systems the tolerance can be controlled because the signal voltage is only fluctuating between the two levels, whereas in this case the signal voltage can take any value. Okay, even if the parameters of the components, like in the transistor you have seen that with respect to temperature or with respect to aging, all the parameters like the H parameters or its reverse saturation current, that changes. Okay, so as a result it becomes difficult to control the performance in analog systems, whereas these systems, they can be, DSP systems can be easily handled, or you can say they are more robust to noise, okay, or fluctuations. And one more thing is that it is more easy to store the digital data in, you can say, magnetic devices for the X. You can store in the CD or in the other digital magnetic device, so or DVDs. So analog signals storage is also a problem in the analog signals. Okay, but the major advantage of DSP or ISP is that you have a flexibility in the implementation port. You can implement in the hardware or in the software. Okay, but then there is a limitation of DSP also, and that limitation is basically called as finite word length effect. Okay, what is finite word length effect? See, you have a DSP system, you have now an analog signal, you have a to D conversion, then we have a DSP system, which may be in the form of a hardware implementation, or it may be a DSP processor. And then you have digital to analog converter, you get a processed analog output. Okay, now this DSP processor that you have, it has a finite word length. Okay, word length means that how many bits you can process at a time. It may be a 8-bit processor, it may be a 16-bit processor, or 32-bit or 64-bit. Okay, now because you have a finite word length, what happens in this part, when you convert A to D, you have an analog signal here. You have an analog signal xt. Okay, continuous time. What we do first to convert this into a digital, we first sample it. Okay, so sampling means we are taking the amplitude at discrete intervals, not continuously. So you have signal at this time, then at this interval you have another sample. This is how sampling is performed. So you are taking the samples of the input signal after every time t, capital T. So this, how to choose this t, that we will discuss when we discuss the sampling theorem. So your discrete samples. Okay, so time is now discretized, and this is basically done by a circuit which is called as sample and hold circuit. Okay, the sample and hold circuit, it actually acts like a switch. That means at any particular time, it samples it and it holds this amplitude till we get the next sample. Because to convert this analog signal into digital, you require some time. So till that time, you have to hold the signal amplitude till this sample is converted into a digital format. Then we sample the next amplitude and we hold this for some time till we sample the next sample, and then that is again converted. So it acts as a switch. So you sample it, you keep it on hold for some time, then at this time, next when you sample the next sample, between this time, this sample will be converted into the digital format. Okay, so this is sampling. You take the discrete samples of the continuous time signal, and then you have quantization. Okay, now what we do in the quantization, we have to now discretize the amplitude axis. Okay, and how you discretize this amplitude, you have, we divide the amplitude of this signal into certain number of levels. Okay, and those number of levels, they are defined by the resolution of your A to D converter. Suppose you have a 4-bit A to D converter, so you can have 2 raised to power 4, that is equal to 16 levels, 16 amplitude levels. So you have 16 amplitude levels on the amplitude scale. Now at any time, at suppose this time, this is the actual sample value. If it matches with a predefined level, it is okay. If it does not match with this level, you have to round off this to the nearest value. So this value will maybe go here, it may come here, depending upon which is nearest, and this is now the error in the amplitude. This is what is called as the finite wavelength effect, or it is called as the quantization error. So this error you cannot remove in DSP. Once it goes into the DSP block, you cannot recover this error. Okay, and this is error is because you have the finite number of bits. Each sample has to be represented using a finite bits. So if it is 16, it means 16 levels, it means each sample which has some value, it can take either this value 0, 0, 0, 0, 0, 1, or it can be 1, 1, 1, 1, 15. So this is voltage level 1, voltage 0, 1, 2, 3 up to 15. So at any point of time, so if it is suppose 0.1, if the signal amplitude at any time is 0.1, but 0.1 is not a level, so you have to truncate this, round off this to its nearest value. It means it will go maybe to 0, that is 0, 0, 0. And this is what is done in the final stage, that is your binary coding. So after binary coding, for each sample, you get a binary number. If this is suppose any sample value out of these 16 sets, so you may have this value as 0, 1, 0, 0 suppose. So you generate a 4-bit code for each sample. For this sample, you again have a 4-bit code, maybe 1, 0, 1, 0, anything, and so on. Okay. Now this finite word length effect, it can be minimized if you increase the word length. That is, in place of 4 bits, if I use a 8-bit processor, so my number of levels will be 2 raised to power 8, that is 256. So these amplitude levels, now they will come close to each other. Okay, as a result, this quantization error will be reduced. So you can minimize this by increasing the word length of the processor, but you cannot totally eliminate it, and it is a irreversible error. Okay, you have to tolerate this error in DSP, which is called as finite word length effect. Okay, so you have a continuous time analog signal, you have a sampler which samples the signal at discrete intervals of time. You get a discrete time but still analog signal. Okay, and then you quantize these amplitude levels, you discretize it depending upon what is the chord length. So you get a digital value for each sample. So these values, they can now take only one of those levels which are already defined in this set. And then finally for each sample we generate a binary code. So finally you get a signal or the output of this in the form of zeros and one, which is a binary signal and which has to be processed by a DSP system, right? And this finite word length effect, one more important thing is that this error comes during analog to digital conversion. Okay. Another important effect is that this effect can be within the system itself. Okay. Now we have a digital signal at the input, you have a digital signal at the output, and before this we have done A to D conversion that I have not denoted here. So one error you get here because of this A to D conversion, that is quantization error. So xt was converted into xn, analog to digital, and because of the finite word length of the processor you have some quantization errors here. Okay. Now another source of error can be the system itself, right? When you design a DSP system, maybe suppose I simply take an example of a filter. Okay. So a filter is a device which is used to remove the undesired components from the input signal. Suppose I take an example. You have suppose a ECG signal. When you record the ECG signal from the human body, it is generally corrupted with 50 Hz power line interference, PLI. Okay. So this is your input signal xt, which is signal plus noise. So you have to design a system which is in this case is a filter to remove this noise from the signal so that at the output of this you get a clean ECG signal. Okay. Now this filter, it can be analog filter, it can be a digital filter. Okay. If you directly give the analog ECG signal to a analog filter, that filter may remove this 50 Hz interference. In that case you need to have a filter which has a frequency response like this notch filter. Okay. At 50 Hz frequency you must have a null point or a dip 0. So this frequency will be removed. The rest of the frequencies they are passed by this filter, you get a clean signal. Okay. But if you use a digital filter, in that case now you have converted this signal which is analog signal into a digital signal. Okay, which is a mixture of two components, a pure ECG signal plus suppose a noise at a frequency of 50 Hz. So you design a digital filter for that case. Now digital filters, they are totally different from analog filters. There is a complete unit on this that we will discuss, how you convert analog into how we design digital filters. Now when you design a digital filters, you have two types of systems, finite impulse response and infinite impulse response systems or filters. So when you design a filter, you have some filter coefficients, whether it is FIR or IR filter, you have some filter coefficients, and based upon the filter coefficients, this filter processes the input signal and you get a output signal. Okay. Now suppose you are designing a filter to remove 50 Hz noise from the input signal, and for this you are using a FIR filter or IR filter, and you are getting some filter coefficients. Suppose the filter coefficient has a value maybe 0.01 to 0.10101. This is a very precise value. Okay. But when you are going to implement this filter using a DSP processor, you have again to represent this filter coefficients with the finite resolutions. That means if it is 8-bit processor, the filter coefficient will be stored in the memory using 8-bit format only. So there may be a possibility that you have to truncate this filter coefficient value. It means what you have actually designed is this value, but what you are going to store may be only this value. Okay, you may be able to store only this much of information. So these bits, these values, they are discarded now. Okay, this may be for any coefficient. Okay, so for some coefficients which may be integer values, or which are not having too much values after the decimal point, they may be accurately represented by the word length of the processor, but for some bits you may have to truncate some of the values of decimal. So what happens is now that the filter that you have designed and the filter that you are going to implement, they are somehow different. So as a result, the frequency response of the system will also change, and because of the change in these coefficients, the pole zero plot of the system will also modify. Okay, the pole zero plot, when you have studied Z transform, this plays an important role in the stability of the system. You have a unit circle of radius 1, and when you plot the poles and zeros, you may have a 0 here. The zeros can lie anywhere. Okay, but the poles must be inside the unit circle. This is a condition for the stability of discrete time system. If any pole is outside the circle, the system becomes unstable. Okay, so suppose you have designed a filter or a discrete time system in which one pole may be lying very close to the unit circle. Okay, maybe you have a pole here at this point at a radius of 0.99. Okay, right now, since this pole is inside the circle, your system is stable. But when you apply the finite word length effect, the filter coefficients, they may get changed, and if the filter coefficients gets changed, there will be drift in the pole zero plot, and there is a quite possibility that this pole may move outside the unit circle, suppose at a radius of 1.01. Okay, this drift is possible, and because of this, the system will go from stable to unstable. Okay, so study of finite word length effect is very important when you will study the IIR systems or IIR filters, because FIR filters, they don't have any stability issues. They are always stables. They don't have any poles basically. But when you have IIR filters, they have zeros as well as poles, and you have to make sure that all the poles, they must lie inside the unit circle for that system to be a stable system. So whenever you design any IR system, you have to study the effects of finite word length before you implement it. Okay, so this is a general overview about what is basically DSP. So in the first, I was discussing what we are going to cover in this. So we will study some basic review of signals and systems. So we will study complex exponential and sinusoidal signals in more detail because they will act as a building blocks. Then some system properties, we will just revise in maybe 1 or 2 lectures all these basic concepts. And sampling, we will discuss in more detail how to convert a continuous time into a discrete time signal. And then there is a different concept of frequency in analog and digital. That is very important. Before you study the systems, you must understand what is the basic concept behind the frequency in analog and digital system. So this is, we will cover in the first unit when we study the basics. The second part of this will be the, we will study now the frequency analysis. frequency analysis. In the frequency analysis, you have Fourier, or in general we will study the transforms, which is a core topic again in DSP. So there are different transforms that we already have studied. You have Laplace, you have Z transform, you have Fourier transform. Okay, this you may have studied in your signal system course. We will focus on two major transforms and algorithms. One is a DFT and another is your FFT. These are the major topics: discrete Fourier transform and the first Fourier transform. Okay, and FFT is basically not a transform. Actually, it is an algorithm which is used to compute DFT in a very efficient manner. Okay, so in the frequency analysis, we will start from a overview of Fourier. See, when you study this Fourier analysis, we will study in some more detail, but I am just giving an introduction. What is this? We have two things in the Fourier analysis. One is your Fourier series, one is your Fourier transform. And again, this Fourier series, it is defined for continuous time signals in a different way, discrete time signals in a different way. So we have continuous time Fourier series and discrete time Fourier series. And the same is in the Fourier transform. We have a continuous time Fourier transform, and then we have a discrete time Fourier transform for discrete signals. Okay. Now from this DFT we generate DTFT, we generate DFT, discrete Fourier transform, which is nothing but the sampling in the frequency domain. Okay, when you sample the discrete time Fourier transform, we get the DFT, and when you implement it using the FFT, that is first Fourier transform, this is very fast implementation. Okay, this is an algorithm which is used to compute DFT in a very efficient manner. So these two topics we will discuss in more detail, but before that we will give the overview of these also, what you have already studied, what is Fourier series and how it is different from the Fourier transform, and what is the utility of these in signal processing. Okay, and then after that your next major topics in this will be digital filter design. So digital filter design is totally different from analog filter design. So we will study two types of filters in this: finite impulse response and infinite impulse response filters. Okay, and there are different methods for design of this system. There are different methods for design of IIR systems. Okay, and then we will see the implementation of these filters and these systems, how the discrete systems are implemented. So in the implementation part, you will see that for any discrete time system, there are three basic operations. You have a multiplier, you have a adder, and you have a delay unit. So DSP systems, they are very efficiently implemented using just basic three operations. So you delay, you multiply, and you will get add, you get the outputs. So there are different structures, implementation structures for FIR filters. There are different implementation structures for IR systems. But before designing this filter design, we will just take a look on what is FIR and what is IR. These are also classified as recursive and non-recursive systems, and how they are different. Okay, and how then they are going to be implemented. And finally, at the last, if time permits, we will give an introduction to DSP processors. Okay, so this is what is the course outline. We'll start from some basic theory of signals and systems, the classification of signals, the concept of frequency in the analog and the digital domain, and what is the differences between the continuous time and discrete time complex exponentials. Okay, then we will discuss about some basic properties of the systems, how the discrete time systems they are different from your continuous time systems and how they are implemented. And then we will discuss this Fourier analysis, the DFT and FFT in more detail, but with the background of the Fourier series and Fourier transform. And finally, we will discuss about the filters. There are different methods for finite impulse response and infinite impulse response filters and how they are implemented using different structures. Okay, so this is for today. Thank you. We will continue in the next lecture with the some basic concepts of signals and the concept of frequency in continuous and the discrete or analog and digital domain.